Hello everyone! Today I would like to show you how to plot some Feynman diagrams. Before we start, you should know that we will be plotting time and space in a two-dimensional graph. Now there are two variations of those graphs, so I'm going to show you the two possibilities. Well, you either have your time in your y-axis and your space on your horizontal axis, or vice versa. It doesn't really matter as long as you're able to recognize the processes which are happening or to draw them to describe them. Depending on the question, on the bibliography, on the author, you'll see each different situation. But in this case now, we will be using the first one for most applications that we have here. Now, before we move forward, let's establish some standards here. So, quarks or leptons, they will be represented by solid lines. So up quarks, for example, or electrons. Exchange particles, they are usually drawn as wavy lines. So gamma, W minus boson, W plus, Z boson, any of those would be represented like that. Sometimes you may also find dashed lines. It's also another representation. Gluons, which are also exchange particles, they're a bit different. So they're represented by curvy lines like those. Antiparticles, they will be drawn as if they were going back in time. So in this case here, since time is growing as we go up, an antiparticle would be drawn going downwards. For example, here, an anti-electron. Now, last but not least important is that in every vertex, there should be lines going in and out. So if there's something going in, there must be something going out. So this will always work. So let's take a look at this example here. Electron emits a photon. So as time is passing, our particle is traveling through time and space. So, well, it's an electron. So it's a solid line and going on the positive direction of time. Now, at some point, it will emit a photon, curvy line, okay? And since there is some release of energy here, there will be some loss in momentum. So the particle will tend to go back in space, right? It's just like, for example, if you're in a skateboard and you're going forward, but you throw something forward, then you slow down. Or if you throw something backward, you will accelerate, right? It's the same principle. So that's the simplest case that we may discuss. Observe here that we do have a vertex and there are arrows going in and arrows going out. So we're not violating our rules before. Now, what would be the difference if this was an anti-electron, so a positron? What would be the difference? So just for the sake of comparison, I'm adding another graphing area here. So positrons, or any antiparticle really, will be drawn as if they were going back in time. So in this case, it would be going down. Since time grows up, it would emit a photon and then lose some of its momentum. Now, what if we were discussing about a pair production? So, in this case at first, we only have a photon just wandering in space, and then suddenly it's going to produce a pair of particles. So there will be two particles here. One will be drawn as going in and one will be drawn as going out. The one which is drawn going in is going against time. That should be our positron, our antiparticle. The other one, which is going positive on time, is our electron. So there you go, a pair production, particle pair production. Now, most likely in your exams and the problems that you're going to face, you will not visualize those circumstances alone. You're going to merge them together and actually look at larger problems, such as the one that we're going to look next, when beta decay happens. So in a beta minus decay, a neutron turns into a proton because one of the quarks change. Let's remember what is the quark structure of a neutron and of a proton. So a neutron is composed by up, down, down, whereas a proton is composed of up, up, down. So what's actually happening here is that one of those quarks, a down quark, is turning into an up quark. When that decay happens, an exchange particle called a boson will carry that message away from the particle. And that boson will then turn itself into a antineutrino and an electron. So let's start sketching our Feynman diagram here. Coming from the bottom, I will have my neutron, which is my original particle. So this is the path that my neutron is traveling. However, now we're going to express each of those quarks. They're traveling together, yes, but we're going to draw 3 separate lines here, each of them representing one of the quarks in our neutron. So originally it's up, down, down. And then what happens is that this down, let's say, will turn into an up. Everything else is the same. Up, down, up. Now up, down, up, or up, up, down, the order here doesn't matter, is a proton. So yes, we get a proton and this is our neutron. Now something is going to happen here, and that's what we're going to do now. Now, since this down quark turns into an up quark, there will be some negative charge just vanishing. Take a look at the properties of a down quark and an up quark. The up quark has a charge of plus 2/3 of an electron, whereas the down quark has a charge of negative 1/3, the charge of an electron, or the elementary charge, right? So what's happening here is that when we turn one down quark into an up quark, there is a whole one charge vanishing, and that's going to the electron. So what happens here is that a boson will need to carry that message. So a boson here, in this case, since we do have some negative charge vanishing, this boson will have to be a negative boson. Now this guy, at some point, will then create the pair of our antineutrino and our electron. So notice that we have merged together the examples that we had before. We do have some particle here creating a particle pair, and we do have some charge being emitted here, some energy being emitted, some information traveling here, and those are our force carriers.